So if you have a theory for the big and a theory for the small, and they don't agree with each other, then you get like literally split personality, disorder, and it really has an impact on society. I mean, like your science community, like literally start becoming neurotic. So I started to like dig in, and I show that like actually if you look at the big, right, and you look at the small, and you try to find what is in common between the two, and you dig down. So the big, you get stellar objects that makes galaxy, right? You get galaxy-sized structures is pretty well the biggest stuff we see. That and quasars, which are basically baby galaxies that eventually become galaxies. And then, you get smaller, you go like atoms on the quantum side, stellar objects on the cosmological side. Then you find like stellar black holes, and then the nuclei of atoms, all right? And then when you look at the stellar black hole, when you look at a black hole, all of a sudden you start to realize, wait, you've got this like infinity creeping in the equations, right? So in Einstein's description, basically you find like singularity being present. And then if you look at the quantum side, you find infinities as well. That is, when you look at the energy level that's inside the atom, the space inside the atom, you find that that stuff is, very much going towards infinity, the infinite amount of energy. So you find this singularity being present in the middle of a black hole, and you find this singularity being present at the quantum level, at the very, very fine level of the quantum level. And these two meet at a length that's called a Planck length, which is 10 to the minus 33 centimeters, right? So like, this is a really important thing. It's not, so basically, so 10 to the minus 33 centimeters, okay, is the Planck length, and it comes out of h bar, which is equal to, which is equal to h over 2 pi. So I want to just go through this a little bit, okay, because I usually don't get the chance to do that. So h bar is the Planck length, the Planck constant, okay. So this is how quantum mechanics emerge, all right. It started with a light bulb, okay. Planck got asked by light bulb of the time manufacturers to find a way to make a better light bulb, because at the time the light bulbs didn't last very long. And so Planck, being a physicist, said, okay, I'll try to figure out how to make an element inside the light bulb that'll last longer. So he started to write the equations to describe the radiation, or the thermodynamics, the heat that, an element in the light bulb will emit, the electromagnetic radiation of a body, right? It's called a black body, a body that would absorb any incident light onto it. How much heat would it radiate, right? And so when he started to write those equations, it didn't add up. The equations, the classical mechanics equation at the time, said that the light bulb or the black body should emit infinite amount of energy, meaning infinite amount of ultraviolet radiation should come out. And that was called the ultraviolet catastrophe. This is what started quantum theory. And Planck was, from laboratory we knew it was not an infinite amount of ultraviolet coming off. So he actually started to think, I'm just going to throw this free parameter in there. I'm just going to throw this constant in there. Because he noticed that when he was running the equation, if he put this little value in there everywhere, it would come out just right to what the experiment was. And he called it, I mean, it was eventually called the Planck constant. He thought it was bunk, though. He thought it was bad physics. He published it, but he said that, you know, there's probably a more elegant solution, but this is all I can come up with, so I'm just going to go with that. And then Bohr realized, and so, you know, this little energy, eventually Bohr realized that if you know, when an electron is on an orbital and it gets popped to another orbital, it's popping in the exact same energy, meaning like so this, Einstein saw this as like a little quantity of energy, and that's why quantum theory is called that way. It's describing a little little packets of energy that space-time is the, and you know, the reason why Planck thought it was bunk is because it describes something very strange. It says that when something heats up, it doesn't heat up smoothly. It heats up in these little quantas of energy. So to him, it sounded like it's got to be wrong, right? It's just that the quantas are so small, it appears smooth to us, but actually it's quantized. And so Einstein, and then so Bohr used it, but Einstein used it before as well, and he actually realized, okay, well, these little quantas of energy might describe, you know, the particle, like that light is like a little quanta of energy called those photons. And he came up with the photoelectric effect, meaning that he said light can hit a crystal and these little balls of energy can knock a crystal, an electron out and make a little bit of electricity, you know, like photoelectric cells, like what we use for solar panels, right? Einstein actually came up with that and called it photons and published that, and this is actually what Einstein got the Nobel Prize for. Okay, they first had to give him a PhD, an honorarium PhD, because he didn't have one, right? And then they gave him the Nobel Prize, but they never gave him the Nobel Prize for relativity. They gave them to him for, you know, the photoelectric effect. And so this actually started quantum theory, and then Bohr showed that the atom absorbs the little quantas of energy, the little photons, and then as a result, it charges, like the energy goes up, and then boom, it pops the electron to the next orbital, and so on, right? You guys are following this, right? And that was the start of quantum. And from the Bohr expression, you know, H, which was the Planck constant, that amount of energy, that energy, was described as H over 2 pi. That means it's an angular momentum. It's something going around by that amount of energy. That amount of energy is a little spin, so it's called a quantum of action. So I want you guys to understand this, like spin is actually present at the fundamental level of quantum theory. It's very, very important, like at the very fine level of structure of space-time, spin is described in a very classical way by quantum theory, but then it goes completely sideways. Like quantum, both with the double slit experiment interpretation, the Copenhagen interpretation, which is completely wrong, and we'll talk about that, and how, you know, the actual, you know, and then like the biggest fudge factor ever, right? Which is, we have a problem, meaning if you have an electron that's going around a nuclei, right, like this, it's spending energy, right? You know, it's a positive thing and it's orbiting a negative thing, right? So like it should go like, you know, so like an electron in the universe, as soon as it was created, within a Planck's second, it should have like disappeared, right? Like no atom should have been allowed to exist. Like the electron should have crashed onto the nuclei immediately, right? So that was the problem in physics. So what they did, and this was combined with the double slit experiment. So I know I'm like giving you a big tangent here, but I'm like trying to give you the basis of where everything went wrong, because like neuroticism just locked in. I don't know what these guys were taking at like in Copenhagen, but like it was bad shit, bro. Like they had the wrong drugs. So it's like, holy shit, really? So then they, at the same time, was this experiment that was made, right? That's called the double slit experiment. You guys all heard about it? Yeah. Spiritual people are really excited about the double slit experiment for the exact wrong reason. I've been trying to explain this. I mean, I've been debating this with like Chopra and Manas and all these guys that like, oh, the double slit experiment explains consciousness. And like, since like, you know, the What the Bleep movie, like this is like, and it's insane. It's like so wrong, it's not even funny, right? It's like wrong as you can go. Okay? Like, first of all, in the standard physics, there is nothing in the double slit experiment that says anything about consciousness. Nothing. So like to say that the double slit experiment, Copenhagen interpretation explains consciousness or says that, you know, consciousness has anything to do with physics is wrong. Like, wrong. Like, and this is why the mainstream is laughing at it. Like, that's why, like, they, you know, they ignore, you know, Manas and Chopra and all the gang, right? Because, like, it's wrong, you know. The physics doesn't say that at all. The Copenhagen interpretation just says that there's a collapse of a waveform in which, you know, when there's an observation, when there's, like, a measurement that is made, right, then the state collapses into its final state. But when it does not collapse into what the observer hoped the thing would be. Like, it has nothing to do with consciousness, meaning, like, it's not because you know, the observer wanted a cat, that the cat appeared. Like, it could be a crocodile. It could be half of a crocodile and half a cat. It could be like, you know, could be a monster from another universe. I mean, it has nothing to do with the observer. Zero. Right? So, like, to make that leap and that interpretation for classical physicists is wrong. And that's why they ignore that stuff and they just laugh at it. Right? So it would be good if those guys, I mean, Manas is like, I mean, he has a PhD in physics. And you know, it would be good if they actually understood that part, that, like, it's not related and it was incorrect for the you know, What the Bleep movie to, like, make that association. And you know, the Schrodinger's equation then, so basically they looked at, so this is what happened. You shoot a photon, an electron at a slit, right? And, you know, you get a pattern on the backboard of, like, dots, right? If you put two slits and you shoot the particle, all of a sudden you get an interference pattern on the backboard as if the particle split, you know, and it was in two states, and then it recombine and interfere with itself on the other side, right? And so then they went, oh my God, the particles can be in two states at the same time, in two places, and then they can, you know, they can be a wave and a particle at the same time. And it's, oh my God. And then they went with that. Since then, they teach physics this way, right? They tell you a particle can be a wave and a particle. They can be in two states, like it's called superposition, right? And so neurotic insanity is occurring in the head of student. Like, oh my God, the universe is like something that's completely irrational, that can be anything at any point. Like, and then they put a camera there. And the part is that, you know, they put a measuring device to try to figure out at exactly in which slit the bloody thing went, right? To see if it's really in like two states at the same time. And then they get a third result. All of a sudden get the dots back. And it's like, oh my God, now I'm but the part that they don't mention in the, you know, more, you know, they ignore that part, is that the thing that's measuring, right, that makes the effect that the observer is changing the result, the thing that's measuring has to be tuned to the size of the slits. It's not just any measuring device you can put in there that gives a different result. You have to tune the device to, you know, it has to be all worked out. Otherwise, you don't, right? So that's something they omit to mention. You guys see what I'm saying? So basically, there was a person in Copenhagen that tried to explain to Einstein and Bohr and all those guys, wait, you know, you don't need to go like into quantum insanity, right? And like make the world, because basically for 100 years they've been teaching everybody, don't try to visualize it. It's not anything you can visualize. It's not mechanical. They abandoned all mechanical things. They took Schrodinger's equation and made it into something that's like a probability curve. So like only physics at the quantum level can only be written in terms of probabilities, right? It's all based on randomness, meaning like, that's why I'm saying it has nothing to do with consciousness, because it's not based on the conscious observer producing anything. It's saying that like it's completely random and you don't know anything about any state until it's measured. And then it claps into something and you have no idea what it's going to be, right? So that the typical example is a cat in a box, right? It's called a Schrodinger cat, right? It comes from the Schrodinger's equation to describe this. And I hope you guys are following me. It's really important because it changes a lot of things. It goes, I'm going to go from completely neurotic insanity to actually like, no, actually it's simple and it's mechanical, okay? And it's fluid dynamics because, you know, the world is all fluids, dynamics, and friction. You know, that's how babies are made, you know. But, you know, and so it has to do with like, so basically they went like this, they went, okay, so if you have a box and you have a cat in it, this is what quantum theory is based on. Like, just check this out. And you have a vial in there full of poison, right? And there's a hammer in the box. I mean, like, this is remarkable. This is remarkable. This is when the galactic community goes, oh my God. And then they have a hammer in there, and it's on a random generator, right? Which no such thing has ever been found, but never mind that, right? Like, we haven't found anything that actually is completely random. We can't find anything that, you know, even in background noise in the universe, we find like patterns, right? So, but let's just assume there's like such a thing as an ideal random generator. Then you know, the random generator is attached to the hammer, and like the hammer will only fall when the random generator like outputs something like specific, but you don't know when that's going to happen at any point. Could be any time in the universe, right? And so, and then the box is closed. So since the observer is outside the box, you don't know if the cat is alive or dead. In the quantum theory equation, the cat is alive and dead at the same time. It's in state of superposition, like it's in both states. And it's like, really? holy shit. No, seriously, you guys, because you're confused about the state of the cat, you actually believe that the universe is confused about the state of the cat. Like, is this like human-centric or what? Like, you really think that because you're confused, the rest of the universe is confused. And you think because it's in a cardboard box, the universe is unaware of the state of the cat? You've now isolated it from the universe? Are you serious about this shit? Really? Oh my God, you guys actually did 100 years of physics and a whole civilization on this crap? I mean, like, subsystem, like, I'm like, oh my God, what about the flea? What about the flea on the cat? Is the flea confused about the state of the cat too? You know, because the flea is an observer. What about the frame of reference of the flea? What about the microbe on the cardboard going, yeah, there's a cat? So who gets to say if it's alive or dead? The flea or the human that's confused or what? Like, I mean, subsystems, right? I have been mentioning this. It's in my quantum, in my biophysics paper in the introduction. I'm like, I don't say it so bluntly, but I'm like, what about subsystems, right? Sutskin, one of the best physicists on the planet, just mentioned it in his paper that he just published. Like, we have a problem with subsystems. Like, no kidding, like, you guys didn't think of that before? Like, so...
was he at this convention with all these 70, 80-year-olds, this guy that you're talking about?
No.
Just published this? No.
Yeah,
But there must have been one of those guys that has been teaching this forever that expects somebody to make that jump. Surely they can't think that that's the end of it. So somebody must have been delighted with what you were saying.
Oh,
In that group
no.
of old people.
No. No, they kicked me out. They kicked me out. They said, okay, the busboy's got to go. Yeah, this has got to go. Yeah. Now they, like...
But it's the same for too long. They know something has to graduate somewhere along the line.
Yeah, but they're not willing to go backwards. In their mind, this is known physics, this is accepted, this is the way things are, now we move forward, and nobody wants to go back and say, wait, maybe we made a misinterpretation over here, right? So it's always the same problem, and but the thing is that in Copenhagen and during those years, there's this guy, de Broglie, which is like very well respected physicist of the time. He wrote the equation for wave functions, like, he's expert at it. And he went and talked to Einstein and Bohr and all these guys and said, wait, I can describe the double slit experiment with fluid dynamics. Now, I didn't know this at the time. 20 years ago, I independently said, wait, the assumption is that when you shoot the particle at the slit, that's in a free field, meaning that it's in some kind of a perfect vacuum, that the particle is isolated from everything else. But it's not. When you what if the particle is actually part of a field? Just like a boat, right, on the ocean makes wave when it moves, right? So yeah, it's a particle and a wave, but it's not such an esoteric, crazy concept. It's just because when it moves, it makes waves, right? So if you have one slit, it just get the particle on the other side. But if you have two slits, the wave that the particle makes go through the second slit, interferes, and you get interference patterns. Like, oh, really? And then, and I came up with that on my own, like 25 years ago, like Joe Blow in the van over there, like, oh yeah, that would work. And then, of course, if you put an instrument and you're measuring, when you're measuring, you're making waves in that same field. So then these waves interfere with the waves that the particle are making, and now you get a third result. Dude, really? The cat is alive. If the universe is needing a live cat, it's got one. If the universe is needing a dead cat, it's got one. Like, it's not like everything is interacting with everything and changing everything. The flea on the cat is, you know, participating in the field interaction. You know, the microbe on the box is participating in the field interaction. You are participating in the field interaction. And if you're confused, it doesn't mean the rest of the universe is confused. Like if the tree falls in the forest and you're not there to hear it, the universe really doesn't care. It really doesn't give a shit. It's like it's got all kinds of other things, birds and like ants and all this stuff. They all are hearing the tree fall. And if you miss it, it's kind of like too bad, brah. You know? And so, you know, and the problem is that the spiritual community latches on to the double slit experiment as like this is the proof that the observer is important, but for the wrong reason. And so then it gives you the wrong picture, and so then it actually propagates more neurotic insanity that like physics and science and the physical world is this crazy like esoteric thing that you can never put your finger on. When in fact, it's actually just all fluid dynamics. You know? Yeah, absolutely, and exactly, and but as well, it was a really, you know, you gotta put it in the context, you know, of the time, you know, the war and all this stuff. Like people were trying to find a way to like break free of, you know, mechanics, and you know they wanted like to like just go wild and just write crazy mathematics, and like it was like we want to be free, right? And so there was this impetus to like let go of all previous mechanical, you know, models and get a sense of freedom and just go to like complete statistical analysis and, you know, and get rid of any mechanical physical model.
So what's the right conclusion?
Well, the right conclusion is that it might. Around here, you wouldn't doubt it. I mean, it's like, it's amazing we're still alive to talk about it. But, you know, the right understanding is that there's a field that's interacting with everything. And that's coordinating all events, meaning that there's information exchange across all systems, across all frame of reference that makes reality what it is. It's not, you know, an observer is not like a human being. It's not a cat. It's not a flea. It's the whole thing. It's every atom observing the universe from its own perspective, feeding information to the field that makes up the field what it is, you see? So then you start to feel the connectivity, you start to feel the relationship, the interaction that makes up reality. Right? And now you can start to write physics in a completely different way. Right? So that the start of quantum theory is correct. But where it went because of the interpretation of the double slit experiment went sideways.
When did that experiment come? When did they do that? The double slit one?
Well, that was initially I'm sorry, 40s. And yeah, in the 40s, and I think that the Copenhagen meetings were in the 47, or I'm not sure exactly what year it was. I could look it up, but I can't remember. But basically as well, what happened with this interpretation is that, okay, they start to tell people, don't try to think of the atom as a mechanical object. Don't try to think of the atom as anything you can visualize. Particles can be here or not here. You know, there's uncertainty, so then the uncertainty principle came in, you know, about the position of an electron in the universe. Could be here, could be on the other side of the universe. We don't know. And that's that to a certain extent is true, meaning that if they try to write the math to the position of an electron, if they figure out where it is, they don't know where it's going anymore. It could be going anywhere. If they figure out where it's going, they don't know where it is anymore. It could be anywhere in the universe. There's uncertainty. Now, the problem, that's true. However, the problem is the interpretation of why there's uncertainty. There's not uncertainty because quantum physics is like this woo-woo thing that's floating in the air that has no mechanical function and that you can't figure out. It's true because what you're dealing with is connected to everything else in the universe. It's in communication. So, of course, when you write the math for it, you don't have math that actually can tell you exactly, because like, yeah, the electron or the proton could be here, but the information of that thing is actually as well on the other side of the universe, because it's connected. The whole thing, we're going to see the math for that, right? So does that clarify it, the difference between the two? And so it went just a little bit sideways over here, and it brought us to like this completely alternate view of the mechanical functions of the universe. And people, when I say that, they go, oh, mechanical sounds so boring and linear and all this. Man, mechanical is non-linear. Spin is non-linear, like fluid dynamics, like this is beautiful. This is how beauty emerges in the world. It's nothing like to spit at. It's actually an amazing thing. So now we get a really good sense of how small the Planck is relative to our scale of reality, right? So that even if you were to shrink yourself to the proton size, which is extremely teeny, you would still have to zoom in billions and billions of times before you would start to see the granular Planck structure of space-time, right? Like it would still not be apparent to you, even at the proton level. You wouldn't necessarily be aware of the Planck scale. So this is really kind of the point of the thing, is that space-time at the very fine level is not smooth, right? It started to become clear to me that like space-time, Einstein describes space-time as smooth because he described it as like mathematically as a surface that's curving where there's gravity, so that if you have a ball on a trampoline, then the surface of the trampoline curves. If you put another ball, it appears like it's being attracted, right? He described that surface in terms of a smooth continuum, right? Just like the surface of water in your bath, when you pull the plug, looks like it's curving. And if you still use rubber duckies, if you put the rubber ducky near the plug, then it starts to orbit. Right, and it looks like it's being attracted because the water is curving. So, but it turns out that at the very fine level, it's actually very much quantized. So it's discrete. In physics, we call it discrete. It has discreteness, right? So now you get like a sense of the unification, because we're talking about space-time, which is cosmological, and then we're starting to realize while actually it's quantized. So now you have both. You have the large, smoothness at the large scale, but at the very fine scale, it's actually quantized. Just like water is smooth, the water looks smooth, and it looks like one thing. When you jump in, like we just did, you don't feel the water molecule as separate things, but we know that if we zoom in long enough, then we start to see, they're actually separate molecules and separate atoms and so on, right? So the same thing. So then if you actually calculate how dense this Planck fluid is, and you can literally call it a Planck fluid, because it acts like a superfluid, like a plasma. There's California. This Planck fluid is actually, quite dense. So if you calculate, so if you have a centimeter cube of space, and you calculate how many little Plancks fits in there, because it's so small, of course, in a centimeter cube, there's going to be a lot of them. There's actually something like, 10 to the, I think 10 to, 10 to the 9, something like 10 to the 99 Plancks in a centimeter cube of space. So that's 10 with 98 zeros, right? That is, it's a huge number, right? If you were to say, well, so 10, that each Planck is 10 to the minus 5 grams. So everybody can imagine, right? A Planck. So remember, it's a little angular momentum. It's a little spin. It's a little spinner, right? So if it has a little bit of, it's like a little energy, a little fluctuation. But the thing is when you talk about fluctuation, people think this, right? Every time you talk fluctuation, people think this, right? Because we've been shown an oscilloscope screen with a waveform on it all this time, as if the universe was making like, one-dimensional waves like this. Like the universe doesn't do that, right? So actually, a waveform, like we imagine light coming to our eyes, and we're always shown these graphs when we're kids in the books, with this waveform coming into our eyes, right? But actually, it's going like this, right? Because this waveform, I used to do this in my talks. I used to have a little string and I spin it. And with a strobe, I could flash it just at the right frequency, and all of a sudden it looked like a two-dimensional waveform. But it's actually a three-dimensional vortex, right? So actually, imagine this having a propagation, and this is actually, a vortex. It's going like this, right? It's a vortex going through space. So imagine the little spinner. You could calculate the energy of that little spinner, how fast it's going, and it's going really fast. Okay? You can calculate how much mass that little energy would have. And that, because of E equals mc squared. So if you do E equals mc squared, you get the mass of the little oscillator. And so one little Planck, so you multiply this by this to get the mass of all the Planck in the centimeter cube, and you end up with 10 to the 93 grams per centimeter cube. So it must be a little bit more or less, like 98 or something. So per centimeter cube. So that's the value of the density of the vacuum of space. Okay, like the density of the energy in a centimeter cube is 10 to the 93 grams per centimeter cube. It's called a Planck density. Okay? It's a non-trivial value. Non-trivial, because it's like 10 with 92 zeros is non-trivial. You might have noticed in like your bank account, like when you keep adding zeros, it improves rapidly, right? It's an exponential, right? So when you have like 4 zeros, it's okay. When you have 5, it's like nice. And then when you have 6, you know, it's like, whoa, that's really good. You can take this chair.
I'm going to take a chair. Can I stand?
Huh?
Are you going to stand?
Yeah, I am. I always stand. 13 hours long, typically. And so this you have 10 to the so you have 6 zeros in your bank account. It's nice. You add another one. It's like, whoa, now we're talking, right? You keep adding zeros. Now imagine like you're at like 50 zeros. Those are large numbers. Imagine at 92 zeros, it's big, because if I take the mass of the universe, so I take all of the stars, there's a few billion stars in our galaxy, most of them, like our sun, looks like a grain of sand beside them, right? The earth looks like a grain of sand beside the sun. Now, our sun, most of the stars out there, our sun looks like a little teeny grain of sand beside them. We took all the stars in our galaxy, billions of stars, right? And then we took all the galaxies in the universe, billions, trillions of galaxies, right? We squish it all into a centimeter cube of space. Okay? Imagine how dense that centimeter cube would be, right? The whole universe, like inside a centimeter cube of space, like it would be really intensely dense, right? That would be 10 to the 55 grams per centimeter cube. Okay? That means you're still missing 39 zeros to arrive to the density of the vacuum. Okay, so like, it's, what I mean by it's a non-trivial value, like I really mean it's a non-trivial value. When this was discovered, it was widely ignored. You know, you would think when they discovered that the vacuum is full of energy at that level, people would have gone, oh, we found God, right? No. They went like, oh my God, how can we get rid of that number? And so, in general, physicists do not get taught this. Meaning, they know about the vacuum fluctuation, about, you know, it's called, you know, the Planck C. They know about this stuff. They know that there's fluctuations in the vacuum, but professors do everything they can to never have to actually pull out the Planck density in front of the students, because they know the students are going to go, why are we not extracting energy from the vacuum, right? The professors just don't want to go there. So the result is that when I publish my papers innocently, you know, like 15 years ago, innocently in the papers, in the introduction of the paper, you know, where you're supposed to give the background on how, you know, you're constructing the theory, I would go, so we use the Planck, you know, we use the vacuum density 10 to the 93 grams per centimeter cube, and I would just go on, right? And I got a hate letter from the director of CERN. Saying, actually, yeah, saying that like my value for the vacuum density was insane, and that like where did I get that number, and and I was wrong, and that he stopped reading it at the introduction, because this is just outrageous and all this, right? I'm like, dude, here is the Wikipedia link. It's in every physics dictionary. Like, try checking it out. Planck density. Like, did you guys skip school during that day or what? Like, and this is the director of CERN. You know, this is how, you know, ridiculous this is, right? I mean, this should be known. So you have physicists that that actually, you know, I mean, majority of them don't realize how critical. Now, it is starting to become, the awareness is starting to be there now. Like, it's starting to become, because even, you know, fairly recently, you still had to argue that this stuff was really there. But now they have experiments that prove it is there, like the dynamical Casimir effect, where they're oscillating two mirror at very high velocity, and they can actually pop photons directly out of the vacuum. Like, they can get energy to come out of the vacuum directly. So very little, but some. And so this so imagine this, like, you guys are swimming in this. Not only you're swimming in this intense level of energy, you're made out of that energy, right? You're made out of that density. So it's like more, like, you know, like the amount of it is remarkable. Like, for you to, like, not just like think like, yeah, I'm part of the universe, but yeah, I am the universe, right? Like, this is literally the amount of information you have in you, you know, exceed all the matter in the universe in terms of information. So that's, like, significant. Okay? So when I was looking, so I made graphs early on, and in my graphs I was blown away that, like, if I went, so you remember how small the Planck is. If I made a graph for the energy levels of system going from the universe to a Planck, so I put the universe here, radius to energy level, and I drew a linear line, like quasars and galactic centers and atoms and, you know, subatomic particle, and then Planck would all line up. So that, like, it was like octaves of division of the structure of the vacuum. And, you know, and one of the data point was atoms, was the nuclei of atoms, protons. So I started to think, wait a minute, like, so that's something you need to know. So if I took the universe, so if I take the universe as we see it right now, and I look at its radius, right? Its radius is approximately 10 to the minus 28. I'm sorry, 10 to the 28 not minus, 28 centimeters. Okay? And the universe, the observable universe. And I put in the mass of the universe is 10 to the 55 grams, and I do 2gm over c squared. It will equal, so, and I plug in, so for m, 2g is, g is the gravitational constant, m is the mass, c squared is the speed of light squared, right? So if I plug in, and this will give me the radius of a black hole, right? Schwarzschild radius. If I plug in the mass of the universe into this equation, I get the radius of the universe. That is, the universe obeys the exact condition of a black hole. We live inside a black hole. Okay? Uh-oh. What happened?
I had a funny experience in a meditation, in a guided meditation where we went through a black hole, and in the end I experienced my body and my cells, and I went down, 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 and in the end each cell was a black hole, and I was a black hole, and everything was collapsing into me.
Wow. That's cool.
Does that make sense?
Yeah, absolutely.
And it just flew all into me.
Right.
Yeah.
Well, you know, there's a funny anecdotal story, you know, that I got from Dr. Val Baker, because she follows these sheikhs that are like, she follows these guys, and one of the sheikhs is famous. I don't remember his name, but I think it was in late 70s or maybe 80s. Some journalists asked him, so what do you think of black holes? And the sheikh answered, what do you mean, the atom size or the big ones? And that's like, oh, yeah, right. And so basically, so the universe obeys a black hole condition. We know the center of galaxies, so as a result of my theory, I predicted that the center of all galaxies would have black holes in the middle, right? The black holes have been found in the middle of all galaxies. Quasars are black holes. All these data points ended up, and so why, the protons, so I was starting to think, okay, so of course the atom must be a singularity, must be a black hole too. So I thought, okay, if that's true, why is it that we don't measure the mass of a black hole for the proton? And I thought, well, okay, so if I take a proton, we are measuring if this is a proton black hole, we're only measuring what the energy that's available outside the black hole, not the actual energy in the black hole. So I thought, okay, if I take the vacuum density and I calculate the volume of a proton, right? The proton is 10 to minus 13 centimeters. It's pretty small. The space inside a proton, the volume of a proton, is 10 to minus 39. And then I calculate how many Planck energy there is inside there, right? I can maybe prove that a proton is a black hole, right? I thought maybe there's enough mass in terms of Planck to prove that the proton is a black hole. And so I calculated it, and the internal mass of the Planck fluctuation inside a proton is exactly the mass of the universe. I went, yeah, definitely a black hole, right? And so, and that's when I realized, oh my God, the thing is holographic, right? I mean, I had concluded to that 20 years prior by deduction, by logical deduction, but there was the math showing that like the information of all other protons in the universe, right, which makes the mass of the universe is the other protons, is actually inside one proton in terms of holographic information. You guys follow me? So that so that all of a sudden I start to realize, wait, so that means that the mass we measure is actually the result of all the other protons in the universe acting on one proton. And that is the equation I got to come up with. It was an insane thought. Because if you talk, I talk to other physicists, like, can we figure out an equation where we consider the mass of all the other protons in the universe influencing the mass of one? And they're all like, I don't think so. You know, forget that idea or go bowling, but, you know, we're not going to be able to write that. And so, because there's about 10 to the 80th protons in the universe. You know, these are huge numbers. The mass of one proton is 10 to the minus 24. It's a very small number. Okay? So, like, you know, how are you going to nail that, you know, with that, all the protons in the universe making the mass of one little proton? I don't think so, right? So, it was crazy. But what I was able to do is I was able to show, and this was the Schwarzschild proton paper. This is the one I got the most tomatoes thrown at me for. Okay? Because I called it the Schwarzschild proton because the Schwarzschild equation is the solution to Einstein that describes black holes. Right? So I was actually subtly saying the black hole proton. Right? But I didn't say the black hole proton. I said the Schwarzschild proton. So, you know, I wouldn't get too many. I thought I'd get away with it. That didn't work. I got caught. But, you know, I was, so what, all the people that like throw me tomatoes, what they missed is that the paper was not there to identify this, like, why, you know, because if you do 2gm over c squared for the proton, right, you know, you don't need the whole mass of the universe to make it a black hole. You only need about 10 to the 14 grams, which is like 40 orders of magnitude more than the 10 to the 24 grams we measured. What the paper was pointing out, that 40 orders of magnitude between this and this is actually was actually the exact gravitational coupling constant. So I'm gonna explain what I'm meaning by that. So what I mean by that is that what the paper was pointing out is if I make the proton a black hole over here and I make the other proton a black hole over here and I calculate the gravitational force of these two protons pulling on each other, these two black holes proton pulling on each other, it's exactly the strong force. I'll call this F. So the strong force is a force that was invented by the modern standard model. Meaning that when we discovered protons, they have the same charge, right? They're positively charged. So they have to repel this electrostatic charge, push them apart very strongly. So they said gravity is not strong enough to hold them together against the electrostatic charge, so we have to invent a new force. So they invented a new force, they called it the strong force, and they made it exactly equivalent to the force they needed to push them together. And then from there they went on doing physics and assumed that force was there. And since then, that force and gravity don't like each other, right? They can't get the math to like work. In fact, the strong force, they can't even find a formula that gives the right answer for the strong force, even in their model. Meaning, like, there's no analytical solution to that, the solution to that force. They've been running supercomputers trying to find an analytical solution for years. They spent billions of dollars on supercomputer to try to find an analytical solution. There's still $1 million prize to find a solution, right? And it's like, I found it, but like they still ignore it. I'd love the $1 million, you know. But it would help my lab a lot. But they basically said that like the whole thing, so basically they just invented the thing. And what I was saying is when I did the calculation in the Schwarzschild proton paper, when I did the calculation, I could see that, you know, if I did it correctly, very precisely, that value was exact for the strong force. It was exact. It's not like, oh, it's kind of close. It was exact. As far as digits I could calculate. So I'm like, dude, like that cannot be a coincidence. Right? So the proton is acting as a black hole as far as gravity goes, and as far as sucking up the other protons towards it. And, you know, I got in a lot of trouble because they were saying, well, yeah, but your mass of your proton is too heavy. By like 40 orders of magnitude. And I was saying to them, no. Let's do that over again, right? I tried to explain that to them. It just didn't work. I couldn't get through to them. Mostly one guy, you know, Bobaton. Is that actually the standard model threw the strong force in there to make it work without calculate the energy that you have to put in to produce such a force. They just made it appear out of nowhere, and they didn't account for the energy required to produce such a force, and if they did, they would arrive to the black hole proton mass. You know, because mass and energy are interchangeable. You guys see that? So I was like, and so I realized, well, okay, so I'm gonna have to find. In the end of the paper, I said, well, you know, actually, if you look at mass dilation, if you run the equation for the black hole proton and you calculate how fast it's spinning at very, very, very close to the speed of light. And if you calculate it's like 99.9999998 the speed of light, right? And if you calculate at that speed a proton at 10 to the minus 24 grams, and you calculate special relativity says that when you get close to the speed of light, mass increase, right? So when mass increase, like because it's called mass dilation, I calculated at that speed how much the mass would increase, and at that speed the mass increases exactly to 10 to the 14 grams, meaning the proton becomes a black hole. So, and this is why, it's because they ignore the spin. Because remember, they went all esoteric on quantum physics, and all of a sudden it's not mechanical, and although they have spin in there, it's half integer spin, it's not actually real spin, it's not mechanical, it's, you know, they went all like, we don't care about physics anymore kind of physics, right? And so, but I still had to somehow explain how is it that we only measure 10 to the minus 24, because that is the rest mass, right? The rest mass of the proton. So when we measure it, is because we knock that thing, we collide a proton with another, and knock that proton out of the nuclei, and now that thing is no longer spinning anywhere close to the speed of light. And so the mass dilation goes down, and that's its rest mass. You guys see what I'm saying? So
no, I don't see it. Because,
Yeah, I just sort of got lost there.
okay.
If we measure the weight or the mass of a particle, we say there are so many protons inside, and those protons still are moving. Why do we measure the not the correct mass?
Right, but that's the thing. We measure it in relationship to all the other masses that we measure, right? So these are relative mass, right? We measure gravity far from the source of a black hole. So we measure weak gravity. We don't measure high gravity near where the proton to proton interact. That's the high gravity. We measure in the weak field, far from where the proton, unless we knock it out, right? And then we measure what we call the weak, you know, in the weak gravitational field. Do you understand? Yeah. So it gets weaker. So I started to think that way, right? So for instance, if you...
So the
Yeah.
real numbers at the event horizon,
Yeah.
that theoretical.
At the horizon of the black hole is different than in the weak field away from the black hole. So for instance, in our current physics, we think gravity is the weakest force in the universe. How is that possible? Because if you have a black hole, then all the other forces in the black hole get sucked in by gravity, right? The electromagnetic field is weaker than gravity in that instance, right? So gravity is only weak far from the source of the gravitational field, far from the black hole. And so that's what I was starting to tell physicists is that, okay, you know, when you calculate, see, this is the crap that goes on, man. It's unbelievable. So when you calculate, because when Einstein wrote the equations for gravity, he didn't solve them. He just wrote the concept that space-time can curve, right? So, but he couldn't solve the equation. It was too complex. And he published it. And a man called Schwarzschild that was fighting on the Russian front but that got sick and got sent home, found Einstein paper like a few days after it was published, and he started to work on a solution. He said, hey, maybe I can solve it. And when he solved it, it gave this Schwarzschild solution that says space-time, if there's enough energy, can curve into a black hole, into a singularity. And he sent it back to Einstein. And Einstein was really discouraged. He thought, oh, that means my equations, that means my theory is bunk, because I don't believe black holes can exist, right? But he still, you know, but they still found that, like, his equation worked for things, and so they just ignored the black holes until, like, the last 20 years. Until, even when I started to give talks in physics, I would have to argue that black hole exists, because most physicists at the time didn't believe that black hole existed. I didn't just tell them that black hole existed, I told them they were in the center of every galaxy. And that they thought I was insane. And then I told them they were going to see black holes prior to galactic formation if they looked far enough into the universe. And that's what they found now. But I was telling them at the same time that the center of the sun is a black hole, and that the center of the earth is a black hole, and that the center of an atom is a black hole. And then they definitely thought I was crazy, and they still think. They still don't know that the sun is a black hole. And certainly not the atom, although now it's starting, you know, with other physicists going, oh yeah, subatomic particles might be black holes. Go ahead. Well,
is it correct to say that the reason why they're measuring the proton being 10 to the minus 24 is two reasons? One is because they're removing the proton from the nucleus and isolating it, and that they're only measuring the information that it can escape the event horizon, and they're not accounting for the energy density that's inside the volume, just like the water bottle in the ocean.
Right.
It's both things.
Yeah, that's correct. And I'm going to go through that solution in a minute. It's going to become more clear. But I'm just going through a little bit the history, because you got to understand that this is how convoluted it is. Meaning that, like, to this day, so I would argue with physicists, but you guys don't think a black hole exists. Like, for instance, they would say, the sun is, of course, not a black hole. And I'd say, really? Of course not, right? And they would go, yeah, of course not. Look, if I take the mass of the sun and I put it in 2gm over c square, the radius of the sun, if I make the mass of the sun, you know, usually Usually the sun symbol is like a circle with a dot in the middle, which, you know, looks like a black hole. But, you know, if I make that the mass of the sun, the radius of a black hole sun would be, you know, a few kilometers, like the circumference is like 18 kilometers. And they go, you see, the sun is of course not 18 kilometers. You know, never mind the flat earth theory. And so, you know, and I was blown away because, like, I'm thinking, oh my God, you know, I think, like, I must be talking to 2 years old people because, like, it just, like, excuse me, but what is the assumption that, like, all the matter in the sun must be homogeneous? This is big assumption, right? So, for instance, I can take the mass of the sun and say, well, you know, in the sun, the core of the sun is collapsed into a black hole the size of, you know, a basketball, right? And then you have, you know, space, you know, like hollow, and then you have you know, a few million kilometers of plasma orbiting the black hole in the middle, right? Like a galaxy, right? And if you're outside over here on planet Earth, you'd have no idea, because the sun is the exact same mass that we measure. It has the exact same gravitational attraction that we measure, because it's the same mass. It's just that part of the mass is collapsed into a black hole in the middle, right? So of course it's not 18 kilometer, you know, circumference, but that doesn't mean there's no black hole in there, right? It's a huge assumption to think that it's homogeneous across the whole thing. In fact, a spherical body with the fluid dynamics of plasma would not predict that it's homogeneous. And the sun rings like a bell, right? It's like, we have recordings of the sun. If you look on NASA site, you can look for recordings of the sun. It rings like a bell constantly. And that's consistent with being hollow inside, not being full inside. And so, you know, and so I've been working at, in one of my papers, I show this calculation. You take a galaxy, you shrink it the size of the sun, you calculate the rotation rate of the galaxy, and you shrink it for the same percentage of shrinkage to the sun, and you get the rotation of the sun just right. You take a rotation, you know, of the galaxy, and we know there's a black hole in the middle, right? So you take the whole thing with the black hole and you shrink it the size of the sun. That's a lot of orders of magnitude difference, right? The amount of shrinkage you made, percentage to the rotation, is gonna, you can calculate it out. Meaning you can calculate, you've shrinked it that much, the rotation is gonna go up that much, right? And when you do that calculation, you get the rotation of the sun. You get the correct number for the it's within 3%, I think, right? So it's like, it's remarkable, yeah. So you could, from it, but not only that. At the time, in these physics conference, I was saying as well, there, you know, there's sunspots. There are holes on the surface of the sun that are black. They're the size of the Earth in some cases 13 times the size of the Earth. And, and I was saying those are vortices of the material on the surface of the sun that's being sucked in through into the black hole. And they were saying, no, it's just surface events. And now they've had probes look closely and they can see the materials being sucked in. And what comes out of the sunspots? X-ray. This is exactly what happens when particles fall through the event horizon of a black hole. It emits X-rays. And as well, water actually comes out of the sunspots. Like a lot of water comes out of the sun. People don't know that. Yeah. And so, yeah, star water. That is where water comes from. Because it's actually plasma. So this whole thing, you know, that the star explodes and it makes a black hole, this supernova story that they have, this nice story that like a star goes through the cycle, the carbon cycle, and then explodes, goes supernova, and it produces a black hole called stellar black hole. This is what the current views are, that black holes are produced by a star exploding, is so wrong. It's actually the other way around. The black hole produced the star. And the black holes go through cycles in which it explodes all the plasma that it's accumulated. It grabs plasma as it goes around, but as well it produces matter. Black holes don't just suck everything that's around them. They don't. Like this whole story that the black holes are the bad guys just sucking everything up is wrong. Black hole is the source of life. You know, that's why I rewrote black holes, W-H-O-L-E. They're the whole thing, bro. And there's the white holes. The solution to Einstein can give black holes, can give white holes. And then they put the white holes in another universe. They say, oh, the white holes over there, the black holes over here, and then the stuff that falls in over here comes out in the white hole over there. It's like, no. The white hole is around the black hole, right? There's on the outside, the event horizon, there's radiation. On the inside, there's information collapsing. The two are in relationship with each other. That's the feedback. Right? So now we're going to start talking about feedback and random and non-random universe. You see, because that is where consciousness actually lies. So this is what we wrote in that paper. I don't know if I have that paper on that presentation. You had a question over there?
About 1 million.
1 million?
About the sound, the sun is making a sound. So the sound we have experienced last night was what sound does. What does the sound? God, in the Bible they say, in the beginning there's the word. How about the sound?
Mm-hmm. Well, the word is the sound.
The word is the
Yeah.
sound.
So what does the sound of the sun? The black hole has a sound.
Yeah, it has a sound, but so does every planet. Every planet's ring as well. The moon rings. They all ring. They all have sounds.
So black holes have sound. They are tones.
Yeah, absolutely. Yeah, they all ring at very specific frequencies. Yeah, depending on their size and their environment and so on. Yeah.
So you're saying there's different kinds of black holes? Because the ones I've been told about would suck everything, including the light in itself, and just,
No, there's not different kind of black holes. There's just insane physicists on a small planet far away in the galaxy that think that black holes just suck everything. Like, check it out, man. They find a black hole in the middle of galaxies in every galaxy they see. If black holes were sucking everything, how is the galaxy around it? Like, why is there a galaxy around it? Like, it should have sucked it in, no? Like, well, it didn't. Why not? Right? So
would the difference would be between a galaxy this side or a sun or whatever? What makes them different? The spin? I mean, the velocity of the spin?
Yeah, how they were created in the first place.
Or maybe the cycle?
Huh?
Or maybe the cycle?
They're in the different cycles, but as well where they emerged from. So black holes come out of other black holes. just like people come out of other people. It's a very, very, very strange thing, you know. People come out of other people, and so this is it's the same thing. Yeah, and people do come out of black holes, but that's a whole other story. And but this
black holes come out of other black holes. What are the two closest black holes that we can observe?
we've seen black holes like almost touching, orbiting each other.
So like the proton is a black hole and it's there in the cube beside one another, but that space around it, that circumference, it's not collapsing in on itself.
No. So why is it not collapsing? So of course at the time, you know, all this I told them 25 years ago, right? So of course, or 20 years ago, I at the time I told them, well, you know, you guys are ignoring spin, right? Because, you know, they wrote this equation without spin, right? And when Schwarzschild solved Einstein field equation, he was dying. He literally died like a few days after he sent the solution to Einstein. So he said, I'm going to simplify it. I'm going to not take account of spin or charge. So the solution without spin to Einstein field equation was the main solution until the 70s. So everybody assumed that there was black holes out there that were not spinning. If there was anything out there that looked like a black hole, it wasn't spinning, because the equation didn't have spin in it. and this is how I ended up. You see how convoluted it is? That's how I ended up, like, arguing with physicists, because they would go, but there's non-spinning black holes, and I'm like, dude, like, no, there's just non-spinning equations. Black holes spin, of course, everything spin around them, like, and anyway, so of course, now if you had spin, you imagine you have a black hole that's spinning at c, right? It's spinning. So I wrote the equation with spin, and I calculated it, and it was spinning at c. So I put in my Schwarzschild proton that, like, the proton was spinning at c, and I calculated that, or very, very close to c. So imagine the centrifugal force involved in a particle approaching a black hole, trying to fall into it from an object that's spinning at the speed of light, right? Of course, the particle is not able to fall in the black hole. There is a point of balance between the centrifugal forces and the gravitational pull, right? So there's a point in which they can fall in, but there's plenty that cannot fall in, right? There's only a very specific vector in which it can fall in, and that is through the poles. So the whole thing, a black hole absorbing everything around them, is only true if the equation is written so that the black hole is not spinning. Yeah. So now recently they've been able to observe closer to the center of the galaxies, more close than ever before, and they're seeing the plasma around the black hole going at 84% the speed of light. And they're all going, oh my God, particles cannot fall into black holes. You know, they're starting to get that. And so there's actually only very little material that can fall in. And we see material coming out.
Fall in if it's the same velocity and centrifugal force. Like each one of those protons beside each other isn't collapsing into each other because it has the same centrifugal force around it. Is that the strong force that's preventing it from collapsing into each other?
They're in stable orbits. That's right. They're in stable orbits. And if you keep adding protons as you go down the table of elements, all of a sudden you have 100 protons orbiting each other, you know, like more and more and more. Then eventually the orbitals become unstable, and then they start radiating, and that's when you get radioactive material. It's unstable nuclei. You see? And they radiate till they can get rid of enough energy that they can go into stable orbits again. right?
But black holes are pulling some energy in, and if everything is the black hole, the universe as we know it is expanding.
Right,
So
because
then
it's
the next
spinning.
question is, so what we've calculated here is our knowable radius of the universe, and it's got to be bigger than what we know right now. So
It's our observable universe, yeah.
right.
Which happens to be the boundary of a black hole, of course, because that's how fast the light can reach to us. Anything past that, the light cannot reach us, right? It exceeds the velocity of light. You see?
Yeah, but there's got to be more there. It's just that
Right.
for where
But
we
it's-
are in that space and time, that's all we can calculate. to
Right,
reach us.
but it's, yeah, correct. But it's defining a boundary, right? So the boundary condition of our universe.
I think this model holds through even beyond that. I'm not
That's
contesting
right.
that
I
radius
understand.
makes sense or doesn't make
No,
sense. It's
I know.
just that if we're in the
I'm gonna
constant
get that.
expansion
Yeah.
and everything is a black hole, why aren't we receding instead of expanding?
Okay, well, that's the thing. If you so imagine that those are all valid questions. So imagine this. So now I'm going to give you a different picture, but I'm still skipping on stuff. I want to continue finishing, the holographic solution, because that leads to the holographic solution. But here, I'm just going to give you a clue about it, because we're going to get to it this week sometime, hopefully, right? If you have let's say this is the universe, and let's say it's like a galaxy. Galaxy have like huge galactic halo, big spheres that go around, and the stars, they go from the galactic disk into the halos, and then they fall back in, and they go in circles like that. We know that, like Arcturus has gone one loop already, right? And so they go like, the stars go up, and then they get stuck back in and all this. So imagine that's the universe, right? And imagine we're here, right? And we see everything red shifted, meaning we see everything moving away from us. But there's this thing that they keep ignoring, that we see everything moving towards a particular point that they call the great attractor. Right? So they see everything moving away from us, but it's all moving in one great direction that they call the great attractor. And so why? Well, that's because they have this really weird idea about the universe being flat and like insanity. And it's just about as good as the flat Earth. And, so basically, if you go like this, right? So imagine that everything is moving, and here, remember I was saying the only path in is through the poles, right? So the only path in is through the poles, so it's going like this, right? So you're here, everything is accelerating away from you, right? It's all, everything you can see is accelerating away from you, because it's all accelerating towards, the big toroidal singularity, and you're at the equator, and you're seeing, but if we were here, we would see everything contracting towards the great attractor, right? It's because of our position relative to the universe that we're confused about its state. So where was I? Okay, so now, if you have.
So now I can see there's other universes upon other universes.
Yeah, I'm gonna get there. Yeah, I'm gonna get there. Just trust me, I will get there. If I don't, just remind me. Okay, so am I losing everybody? No, you guys are still with me? I've got a few sleeping. Okay. So imagine that, so I was trying to find this solution, right? So you've got the proton, and it's at 10 to the minus 24, but it's only at 10 to the minus 24 because that is the influence of all the other protons on it that we're measuring, right? Meaning we don't see. So imagine that, okay, so let me put it this way. So this is what kept me up for 5 years. Literally, I barely slept for 5 years trying to solve this problem, after I wrote the Schwarzschild proton paper, because I couldn't figure out how to solve it, because I knew I had to express in some crazy equation how all the rest of the protons in the universe were influenced one proton to make it its mass. And the reason I was thinking that is that if you have a proton here, and it's got the mass of the universe in it holographically, and you have the proton here, and it's got the mass of the universe holographically, another one here, and it's got the mass of the universe holographically in it, then that means that they must be connected through little wormholes, you know, and then another one here connecting through wormholes, you know, boom, boom, boom. And then I'm thinking, so that means that the interior information volume inside each proton is the same. Like, the universe is constantly up to date about what everything is doing, right? The whole thing is talking, but then only a small portion of that can come out, because the boundary doesn't have all the information that is inside. So then I start to think it's like a pressure. What we are measuring as a mass is like a pressure of the information being like entropy on the information is what we measure as energy, right? Like the network bogging down at the event horizon, like the throughput is reduced, right? And so I thought, okay, and in terms of spirituality and meditation and all this, it made sense that like the masters are saying, go inside, and then inside you will have access to the whole, right? But on the outside you don't, it's limited, right? And so I'm like, okay, so if I could figure out how to express the relationship of the inside to the outside, and it adds up to the right mass, I got it, right? And I was like, and trying to figure this out for 5 years, right? I literally like walking in circles like miles in my house. My kids going like, Papa is losing it. My wife, I mean, it cost me my wife, you know, like eventually she couldn't do it anymore. I mean, I'm going, and I'm like trying to figure this out, right? It's not, you know, there was some steam, there was some heat, you know, there was some issues. And so and it was, I was calculating a lot, you know, and then when I found the solution, it was so simple, it was like, freaky simple. And I was like, oh my God, I can't believe it took me that long. And basically, I realized, okay, well, if I take,
Did you find that solution? Did you find that solution through calculation, or was it like an aha moment?
I was calculating, and I was actually. It would be nice if it was something that you know, how do you say? Whoa, that might not be a good place to plug. Huh? I wish it was like a very. There was multiple moments. There was one very, very powerful aha moment where I actually understood it at a very deep level, but one of the moments was at the emissary program, sitting on the toilet at like 6 in the morning after all night, going at it, because during the emissary program I thought I had found it, and there was an error that was pointed out by Orion, which is a mathematician that was at the emissary program, that I made an error in the units of my calculation. And that night, I was not showing up the next day at the emissary program without having solved that. So I didn't sleep. I didn't sleep that whole night. I was just like calculating. And then I hadn't found it at like 5:30, 6 in the morning. And so I'm like with my computer, continuing to calculate while I'm sitting on the bowl, doing my thing. And as I was doing my thing, it came, it came out. Exactly. It was remarkable.
We come into the room and you had a whiteboard with a sheet over it.
Yeah.
A sheet, literally. And then I figured it out, and I was thinking, man, this is going to be some historic moment. And this turns out to be the thing that gives him the Nobel. This is the moment where he's going to go ta-da, and he pulled it out, and he was like, check it out. And Orion was like, oh. And we were all like, really? I don't know what that says, but Orion was like, oh, you figured it out.
And then
we gave him a round of applause. He stood up, and we were like, you're going to get the Nobel Prize.
Yeah, and then Orion, from there, like right away, like looked up the radius of the proton that my new equation predicted, and found that it was extremely close to the new value that had been measured in 2010, and then that was in 2010, and then I refined the equation to eventually what I'm going to show you now. Because it actually occurred to me, and when actually it occurred to me was almost a year later after the image, so like how beautiful and simple it was, but and what it was saying, and when I actually got it, like a whole new level of my experience of the universe like occurred in me, you know, and it took me weeks to like. And the whole compound, like we had a fairly large compound in Kauai, like the whole compound, just like everybody could feel it, like what is going on, because it just like the whole thing like went into like, oh, and I was just walking the land in circles for like days, just walking the land in circles, hitting my head with my notepad on my head, going, oh my God, I can't believe it took me so long to figure this out. And it was just powerful. And that's why I like to teach it, because it's really powerful. But, you know, I mean, it's hard to explain those moments. It was really special. And I don't know how to explain how it felt. But it was, you know, I've had many esoteric experiences in my life, but this was something remarkable. I felt I integrated something deeper than I ever did before. And basically I realized that, so remember, you have the proton and you have all the information in it, but then it's restricted by the amount of information that's on the surface. So you could imagine that each one of the Planck structure on the surface is the end of one wormhole that's connecting that specific proton to other protons, right? And then all of a sudden, so now you can see there's only that many throughputs that's able to exchange the information. So there's some limitation, right? There's some baud rate in how much the information can be transmitted across the system. So I scrapped this Schwarzschild proton paper, and I took a black hole, Cygnus X1, and I calculated how many Plancks are on the surface. Now I'm showing a circle for the Planck, but the first thing I did is I said, because I noticed, like all in the equations in physics, the Planck structure was always, you know, L squared, right? Like the way they were tiling Plancks was always L squared, like the Planck length square, which would mean that a Planck would be some kind of square two-dimensional surface. This is actually how the holographic principle in standard physics was written, with Planck tiles that are two-dimensional. And this is why you might have seen in the top of journal like, you know, Scientific American and all this, we may be living in a holographic universe, which is a two-dimensional surface that's projecting a three-dimensional world, right? Did you guys ever see that? Anyway, they talk that way because there's a solution in physics in which they tiled Plancks on the surface of a black hole, and they noticed that a quarter of the value of the Plancks on the surface of a black hole equals the entropy of the black hole, or the temperature of the black hole. And so this holographic approach became popular, and this is how Sutskin won the war against Hawking. So basically this came out because Hawking was saying when information falls into a black hole, it's lost. And Sutskin said that's not possible because in quantum theory, information cannot be lost. No information can be lost. So he was saying that's got to be wrong. And then Hawking bet Sutskin that it was going to be right. And Sutskin eventually came up with this idea that actually when information falls into a black hole, it's holographically imprinted on the surface as Planck bits, right? L square, Planck bits on the surface, and then Hawking calculated it, and it gave the exact temperature of the black hole. So then he admitted to have lost the bet, and and that was really like publicized, and that whole thing happened while those 5 years that I was thinking about this problem. So like the holographic principle that Sutskin had come up with inspired me to, maybe I can describe it in terms of Planck bits on the surface, limiting the amount of information that can come out. I mean, I had the idea, but the fact that Sutskin used something similar encouraged me that like I could actually do that in physics. And so, but then when I look at the way they did it, I was like, wait, the universe is not a two-dimensional surface. There is no such thing. Like, it's remarkable. Physicists make models in their heads and then use them in mathematics and then assume that because they made it in their head and it works in their mathematics, that actually exists out there. Right? So like, there is no such thing as a two-dimensional surface. There is no surface that has no thickness. I mean, it might have a Planck thickness, but it's still thickness, right? It doesn't, the concept of two dimension is a concept of man, not a concept of universe. We say, oh, look, this is a two-dimensional happy face, right? No. The ink has dimensions. The board has dimensions. The only two-dimensional in there is in your brain, right? It doesn't, so the universe is not a holographic projection from a two-dimensional surface into a three-dimensional world. And the universe is not multi-dimensional, like 11-string dimension insanity. It just isn't, right? It's really straightforward. It's zero dimension. It's all dimension, whatever you want to call it. But dimensions is a concept of man in mathematics where we put Cartesian planes to try to calculate things. That doesn't mean the universe does that. The universe does not do that. So what happens is that I say, okay, well, forget the two-dimensional Planck pixel. Of course, if the Planck is something, it's a sphere. So I made a sphere, a Planck sphere, where the radius is the Planck length divided by 2, right? So it would be, the Planck length would be the diameter, and the radius would be half of it. Make sense? And so I extrapolated to a little Planck spherical unit. So I called it a Planck spherical unit. It's in the paper, PSU. So I calculated the number of PSUs that would be inside the proton, inside the black hole, and outside the black hole. So what was on the surface I called eta, right? So on the surface I called eta, and I'm sorry, this is the surface. So I'm gonna make the surface orange, right? The orange is the surface, so that's eta is the surface. And then I calculated the number inside, so that's on the surface. And then I calculated the number inside, and I called the number inside R, capital R. And I basically did eta over R. I did R over eta, right? So that would be the relationship of the amount of information inside the black hole to the surface. It would be a ratio, right? And that ratio I multiplied by the Planck mass to get the mass or the energy of the ratio, to figure out, you know, if that value had any relationship to the black hole whatsoever. You guys follow what I'm saying? Basically trying to figure out what is the ratio of information energy that can come out of that black hole. And the result was the exact mass of Cygnus X1 if I used Cygnus X1. Like if I used that radius of Cygnus X1, I got the exact mass as if I did 2gm over c squared for Cygnus. But in this case, I was just doing R over eta multiplied by m sub L, by the Planck mass, right? 10 to the minus 5 gram, and I got the mass of the black hole. Exact. As if I had solved Einstein's equation for the black hole, but I didn't do any of that. I was just counting Plancks. I was just counting the bits of information in the vacuum. And so all of a sudden, I had mass, cosmological mass, for a cosmological object out of Planck quantum entities. You know, I solved Einstein's equation with quantum theory. So now I was like, the bridge was building, right? I'm like, oh, I've got gravity, but quantized, discrete. So what happened, as I realized, is that Einstein described the water curving with the rubber ducky being attracted, right? And that's really hard to describe because the water curving is like, you know, it's tensors equations and all sorts of elasticity and all this stuff with the rubber ducky going towards it. But what I was describing is the smoothie, right? The water curves because the water molecules are all co-moving in that region of the bath. The water molecules far away from it on the back of the bath are not co-moving. They're more randomly moving, so the rubber ducky is not going anywhere. But when they're organized, when they're smoothie kind of, you know, going, then it produces gravity. But mine was more fundamental than Einstein because the curvature that the water does on the surface is a result of the water molecules spinning, not the other way around, right? So, because, you know, that leads to gravity control, right? Because you can't curve space-time. This is why they tell you that you can't produce gravity because you can't curve space-time.
No, it's ubiquitous, you know, all the way around. It's not going down any hole. Mm-hmm. All that swirling is from every angle, no matter what point you're looking at it.
Right, but
it's not going like this.
Yeah, but technologically, you can't get it to curve or suck in, right? Because you need a huge mass to do that. But what my equations show is that you just got to spin the vacuum. And then you get curve. You know, you just got to pull the plug in the bath, and now you got curvature.
But where's the plug? The plug isn't just here. It's here and here and here and here and here and here. And
no,
here.
but you see, if
and
it's
here and here and here.
Just a minute. If it's incoherent over here, right? And over here it's coherent. This has a gravitational field, right? Right. So it's sucking up stuff, right? Right. So if I want to make this over here, I just got to make the coherency over here. I got to entrain the vacuum to become co-moving over here instead of being the particle being random, right? I got to get them to all play together. And then all of a sudden, I'm getting a gravitational field over here where there wasn't.
You're creating your own vacuum.
You're creating your own gradient.
Okay.
Yeah.
You said you're spinning, so you can create that.
Yeah, so you can create the depression in space-time. And then since you're spinning it, you can control it, you can get it to go anywhere you want. So you can imagine it has huge consequences. Because it basically says you can't control gravity on one side, and on the other side it says, yeah, you totally can control gravity, and you can make your own wormholes, you can make your own, you know, you can like make your own black hole and go across the universe. So, you know, I've got that going in laboratory. You know, I am doing that in laboratory. I have very, very good results so far. Okay? But you'd be surprised how difficult it is to finance a black hole around here. Because they're all terrified they're going to get sucked in, and it's like, it doesn't suck people in. It's just, right? Yeah, we definitely need them really soon. Because that's the source of mass. That's the source. So here, I was basically saying, this simple equation, this simple iteration was saying, oh my God, the source of mass in the universe is the vacuum spinning. It's literally saying that. So that when you look at the galaxy, this vacuum is spinning already. That's what makes the black hole. That proves this, right? What we see as the galaxy is the stuff that's stuck in that vortex of the vacuum that's already present. It's the result that we see, not the source. So that, like, just like coffee, like when you have dark black coffee and you put you spin it in the morning, right? It doesn't look like it's spinning. If you take out your spoon, if it's dark black coffee, you can't see it spin. But then if you put milk in it, as soon as you put the milk, then all of a sudden you see like the little galaxy form, right? It's the same thing. Galactic structures are the dust and the plasma and the electromagnetic field, all this stuck in the smoothie that's already there in space. A star is the exact same thing. That's why there's a black hole in the middle, and so is an atom. And so is a planet. If you calculate the magnetic field at the surface of our planet, it's a 0.7 of a Gauss, I believe, right, on the surface. And you calculate, you know, the magnetic fields drop at the square of the distance, and when they're a high magnetic field, even exponential. But you calculate even at the square of the distance from the surface of the Earth, how strong the magnetic field has to be in the core of the Earth to produce a half a Gauss at the surface. You have a black hole in the middle. You have a pulsar you need in the middle of the Earth to do that, right? Another thing that physicists keep ignoring, right? So this is, I know it might be freaky to think that there's a black hole in the middle of the Earth, but this is actually what's sucking you to the surface, is that black hole, right? And we think gravity is weak because we always measure gravity away from the surface of the black hole, far in the weak field. But near, it's very strong. Gravity is the strongest force, not the weakest force. And they have it exactly flipped.
So if you dug down in the earth, gravity would get more intense?
Well, not necessarily, because as you go down, you got more and more mass above you. So you're going to, as well, get some, you know, pull towards the surface, right? So it will equals out at some, you'll have orbitals. And this is how you can get orbitals even inside black holes. Like there's papers now that have been published showing that inside galactic black holes, there could be whole worlds in there, stable, inside the black hole. And guess what? We're inside a black hole. And we're pretty damn stable, right? You see? So it's actually, you know, it goes on and on. But So then, of course, if I'm like thinking, okay, I got it for the black holes, got universal black hole, is it true for protons? Is it true for quantum physics? And so, it's not wanting to go anywhere.
Maybe we need to get something in our black hole.
Are you hungry? Oh my God, it's 2 o'clock. Okay. Okay, so we gotta eat. Is the food ready? Yeah. Okay. So.
All these distractions.
I know. Food, swimming, having fun out there, vacation time. My God. What kind of class is this? So I guess we'll continue maybe a little after. Yeah? We swim, we eat, we swim, and then we come back. Sounds good? Awesome. Thank you. Thank you, everybody.